So before we wrap up chapter 3 then, let's talk about some typical values for all of these coefficients that we've just derived in chapter 3, starting with the drag coefficients and this coefficient CD0, which is the drag coefficient at the reference condition or when alpha equals 0 degrees. You can see in this table we've separated out these two different types of flight regime. Climb and cruise is different to approach because typically the pilot will deploy the flaps for the approach condition to increase lift and to also increase drag, which therefore slows down the approach speed. So that's why we have these two different versions of this coefficient CD0 in this table. So again, all of these typical values are exactly that, typical values for most aircraft in most subsonic flight regimes. There will be some exceptions to the rule, of course, but if you would like more examples of this, there are some to be found in Appendix B of the textbook. So let's move on and look at the lift coefficients, starting with CL0. So this is the lift coefficient at the reference condition or when angle of attack equals 0. So this is the one associated with camber. So for a symmetric aerofoil, CL0 would be 0, but for typically cambered aircraft, we're looking at, for typically cambered wings and horizontal tails, we're looking at somewhere in the region of 0.1 to 0.4. And then obviously you can see that the lift coefficients due to change in angle of attack on both the wing and horizontal tail are much larger, as you would expect. Also remember that eta h is the ratio of dynamic pressures. We talked a bit about this a little bit in class, and we said that you can pretty much assume that this is 1 unless the airflow is significantly slowed down onto the horizontal tail due to the wingtip trailing vortices and the downwash effects associated with those onto the horizontal tail. If the flow velocity is slowed down onto the horizontal tail, you'll get a value less than 1. If you have a fuselage mounted propeller, for example, that's accelerating the flow, this coefficient will be greater than 1. A couple of other assumptions and typical values on this slide. We can normally assume that the change in downwash with respect to the change in angle of attack is approximately a third. So now looking at the pitch moment coefficients, so the only new one is the CM0 term. So the pitch moment coefficient at the reference condition. So I mentioned this when we derived the equation for it, but this term describes how the wing and body provide a nose-up pitching moment at alpha equals 0. So again, that provides stability in the longitudinal sense. And finally then, let's look at some of these dynamic derivatives that we just derived that arise due to our consideration of small perturbations in some of these variables here. So we talked a little bit about CDU, the speed damping derivative. It's reasonable to assume that that is 0. We also talked about CMU, the Mach-Tuck derivative. Again, we can assume that that is approximately 0. You can see those average values given in the table are negligible, so again, it's safe to assume that they are 0. Then we have all of the terms that are with respect to the rate of change of angle of attack. Again, we assume that CD alpha dot is 0 for subsonic applications, and then finally the bottom three coefficients in this list are the coefficients due to small perturbations in the pitch rate. And again, the assumption that we made for CDQ is that this is approximately 0 for subsonic applications. So that rounds up chapter 3.